So in this chapter, we're going to start discussing continuous random variables. And there's going to be two types. We'll discuss the continuous random variable and then a subset of that, which is a uniform random variable. So the first thing we want to talk about is to recall the difference between continuous and discrete. So in order to distinguish between discrete and continuous, we have to remember that a discrete random variable, or even the word discrete itself, is the countable or finite number of values. And that's like when, like oranges, apples, people, 1, 2, 3, right? Continuous random variable, remember, has infinitely many values, so it could be mostly time, distance, scores on a test, anything that can have essentially decimals. So we can look at it like a number line, and we can think of it too as well as our inequality worksheet that we had. So if we took like a number line, and I just plotted some numbers here, right? So discrete means that if it's not this one, right? Oh, let's call these, let's number these. Okay, so if it's not 0, it has to go to 1. There's nothing in between these numbers, right? So if you had 1.2 of a person, you would have to have 2 people. And so it just takes no numbers in between. It just takes only the whole numbers. Whereas if I drew a number line for a discrete random variable, let's see, then I would have any number in between these integers. So if this was temperature, I could have any number in between, right? A half a degree, 1 degree, 1 mile, 1.5 mile, or 2 miles, 2.1, 2.2, 2. Whatever, 2.001. It doesn't necessarily have to be jumping one from the other. It can be anything in between. And so continuous just means that it can be numbers in between whole numbers like decimals and stuff. Now, there's a little kicker to this, because if we think about this in our number sets here, we can think of the natural numbers, right? Not even including 0, right? Because you wouldn't go up to the register and say, can I buy 0 oranges, right? You would always have to buy 1 orange, 2 orange, or 3 oranges. So the smallest set of numbers is the natural numbers. Okay. And then we have the whole numbers, right? And that's the discrete, the whole numbers. Well, if we have whole numbers and then we start going to these rational numbers, and the rational numbers, if you forget, are like decimals, fractions, a over b, right? That's continuous. So if we look at it a little bit closer, just talking about number sets, notice that the whole numbers, which are the discrete ones, are inside the rational set. The rational set is a larger set. So we could say and argue that, well, if something is continuous, doesn't that include discrete? And I would say yes. So continuous includes discrete values. But in our world, not everything is continuous. Like a lot of things, like a box of crackers is one box. You're not going to be selling one cracker from one box, right? So we have to distinguish between our data because a lot of things in our world are discrete, but we can say that the continuous does include discrete values, but if it's discrete, we will use discrete, which is chapter 4. Okay, so I hope that's more clear of like a difference between the two and then what is in common with both. So now moving toward some examples, we're just going to identify variables to be discrete or not discrete. So if we determine the random variables to be discrete or continuous, state possible values for the random variable. So the number of light bulbs that burn out in a room of 10 light bulbs in the next year. Well, if we think about light bulbs, that we know that I couldn't never install or replace a light bulb with only a third of a light bulb. I can't have half the glass there, right? So definitely is discrete. And then we would be counting, if we had 10 light bulbs, it would be 1, 2, 3, 4, and all the way out to 10. Okay, so the number of leaves randomly selected on an oak tree. So if we think about leaves, if I wanted a whole leaf, right, it would have to be I wouldn't cut it in half, right? So this is discrete. And we would count 0, 1, 2, 3, and dot, dot, dot. The length of time between calls to 911. So the length of time, we definitely could have 3.5 minutes, right? Some of us run, 9.5 minute miles. So the length of time is definitely continuous. And it could be anything like, for example, 1.3 minutes, right? 0.2 minutes. Or it could include some discrete values, right? 5 minutes. Okay, so essentially what we want to think about is when we have continuous data, it includes discrete values, but if our data is discrete, we don't say continuous, we keep it as discrete. Okay, so now let's go in and talk about the properties of continuous probability distributions. So the graph of a continuous probability distribution is a curve. The probability is represented by the area under this curve. So this is really important because we're going to now talk about probability as the way we always should have. And so this starts with now connecting probability with now distributions. So because the continuous probability distribution is a curve, there is going to be some shape. And if we shade the shape, that would be area, and that area that we'll shade is going to be probability. So let's talk about the probability density function. PDF. So the probability density function is exactly what it is, function. I told you that we don't use algebra in this class, right? I said I could count on one hand when we use algebra, and this is one of the times. It is a function f of x, And we use that where f of x is the input and f of x is the output. And essentially, we hardly use it in a function algebraic way. We use it just to represent the function that corresponds to the graph. So the area under the curve is given by the CDF, which is the cumulative distribution function. And the cumulative distribution function is used to use probability as area, or vice versa, area as probability. Okay. So some important properties: that the outcomes are measured, not counted. The entire area under the curve, this is so important, is equal to 1. Why is the whole area under the curve between the x-axis and the curve 1? Well, what is the maximum probability? Right? 100%, or in other words, 1. So it makes sense why that area would be 1. If you want to actually mathematically calculate it, you would need some calculus. Okay, so the next one is the probability is found for intervals of x rather than individual x values. So the probability is found for intervals of x, so less than, greater than, or equal to, right? All those inequalities. So property 4 says if you're looking for a probability between two values, then that is the probability that the random variable x is in the interval between those two values. So the probability between those two values is the area under the curve above the x-axis to the right and left of C and D. If you're finding the probability of x equal a number, that is 0 because you're not shading anything. You're just staying at a value. So the area below the curve above the x-axis between C and C has no width, right? Therefore, no area. And then here, the probability between C and D is the same as or equal to, because it's just area. In area, we don't really count perimeter, right? We count just the shading in between the values. Okay, so let's go ahead and just draw some some general quick examples of what these probability density functions look like. So the one that we will be doing, let me go ahead and get a graph going. Looks like this. And let's say it's going to be continuous all the way through. So that's going to be really nice for us. And here's C, here's D. Remember, f of x is the output. So this is f of x. And if I were to shade in between C and D, let's do it in blue. That would be the area, right? And this whole area of the entire rectangle is 1. But of course we can take values in between because it's continuous. Okay, so then what do other ones look like? Well, other ones don't look so perfect like a rectangle. And this one you should recognize because we did it on our inequality worksheet. And this looks like what we're going to talk about soon, called the normal curve. Essentially, the normal curve is just symmetric around the mean, right? And we call this, let me shade the area. And the area under this curve is also 1. And we'll also take pieces from C and D. Okay, so the difference here, okay, that doesn't make sense. So here, this is the normal curve, and then this is the continuous distribution. And so these are called something, which we're going to talk about in just a moment. This first one's going to be called uniform, and this one is called normal distribution. So We're going to learn about these pretty shortly.